Hello everyone, welcome back to another lesson on measurement. Today we are going to be exploring scale factors. Let's have a look at our concept map for today. So everyone, firstly I'm going to talk about what is a scale factor. After that, I'm going to show you what a scale factor would do to a rectangle. We're also going to talk about polyhedrons and we're going to remind ourselves of what those are. Then we're going to have a look at the influence of scale factors on cubes as well as on rectangular prisms. Great, so let's start off with what is a scale factor. It is possible that the dimensions of a prism are changed. For example, the length, breadth, and height of a rectangular prism may be doubled. This would mean that the volume and the surface area of the prism would then change. The number that each dimension is multiplied by is known as the scale factor. So everyone, all this is saying is that in measurement, if I've got a 2D shape or if I have a 3-dimensional shape, I can multiply certain lengths by scale factors. So for instance, if I have a cube that has sides of length 2 and my scale factor is 2, I multiply each side by 2. So I'll have 2 times 2, so the size of the cube will then be 4. So essentially the scale factor changes the dimensions of a shape through multiplication. Let's look at the next slide. So if I were to use an example of a rectangle and the length is x units and the breadth is y units, then we can write the area of the rectangle as length times breadth. So this is just linking back to some of your previous knowledge that if I have a length of x and a breadth of y, the area of this particular rectangle will be length times breadth, which is just xy. Great. Now I'm going to show you what would happen if I introduced a scale factor to this rectangle. So if we were to decide to now triple the length and the breadth, this means that we would multiply the length and the breadth by a scale factor of 3. So we're tripling the lengths of the rectangle. So we can see that it's now 3x and 3y. So I'm now going to calculate my new area of the rectangle, which has been multiplied by a scale factor of 3. Length times breadth would end up being 3x multiplied by 3y. So my new area would be 9xy. So if I want to look at the comparison between the new area and the old area, the new area divided by the old area would be 9xy divided by xy, which is just going to give me an answer of 9. So I can see that the scale factor of 3 has made the particular area of this rectangle 9 times larger. Great. I hope everyone's with me. So we're now going to look at what would actually happen if I've got different scale factors introduced for this particular rectangle. So just a reminder, I was using the rectangle that had a length of x and a breadth of y. Let's look at our table. So if I said that my scale factor is 4, that means that I'm going to be multiplying the length by 4 and multiplying the breadth by 4. You can see slightly above I've done the scale factor of 2 and I've illustrated that the length and the breadth were each multiplied by 2, which gave me a result of 4xy. But let's see what happens when I multiply by 4. So the length would be 4x, the breadth would be 4y, and the area would be 16xy. Then for the next one, I'm going to have a half multiplied by my length. So it's going to be a half x because my scale factor is a half. Then it's going to be a half y, which is my breadth. And a half x times a half y is going to give me a quarter xy. Then if I look at my length and my breadth, if my scale factor is 100, I'm going to have 100 times x. My breadth will be 100y. And last but not least, my area would be 1000 xy. Cool. But let's see if I can actually make a general rule for this and having a scale factor for a rectangle. If I say kx, because my length has been multiplied by k, and then I move on to my breadth, which will be ky, because I'm multiplying my length and my breadth by a scale factor of k, my area is going to be k squared y. So this lets me make the conclusion that in general, if the length and breadth of a rectangle is multiplied by a scale factor of k, then the area of the rectangle would have been multiplied by k squared. So with these rectangles, you can see that the new area of the rectangle is k squared times the original area. So if I go back to this slide, you can see that the scale factor squared was always making an impact on that actual area. Sorry guys, that should have an xy. I left the x out over there. So we always are going to have the scale factor squared affecting the area of this particular rectangle. Cool. Everyone, let's move on. For a cube, we've discussed previously that the volume is the area of the base times the perpendicular height. So the volume of this cube is L cubed. The surface area of a cube is equal to the sum of all the squares that make up this particular cube. And because a cube is made up of squares, we're going to take the area of 6 identical squares, and the area of the squares is L squared because we know that the lengths are all equal amongst this square. So because there's 6 squares with an area of L squared being added together, the surface area is 6L squared. Great, everyone. I hope that you're with me so far. After the break, we're going to be looking at how the scale factor influences three-dimensional figures. See you soon. Welcome back, everyone. Before the break, I had started to introduce the idea of a scale factor. In this part of the lesson, we're going to focus on what a scale factor does when I'm calculating the surface area and the volume of three-dimensional shapes. Let's go to the next slide together. So, everyone, I'm first going to remind us that the surface area of a rectangular prism is calculated by adding the areas of all of the rectangles that make up the rectangular prism together. So just a reminder, the surface area, I take the areas of all the shapes that make up the figure and I add them together. Now, because it is a rectangular prism, I have 3 sets of equal rectangles, and I find the surface area by saying 2 times the length times the breadth plus 2 times the length times the height plus 2 times the base times the height. And then for the volume of a rectangular prism, we take the area of the base, and the base is this particular rectangle. And the area of the base is length times breadth. And for volume, I multiply the area of the base by the perpendicular height. And my perpendicular height is just h. Now, guys, we are going to see what a scale factor will do to the surface area and the volume of a rectangular prism. Let's first have a look. So if I say this particular rectangular prism has a scale factor of 2, This means that the length has been multiplied by 2, the breadth has been multiplied by 2, and the height has been multiplied by 2. I am now going to calculate my new surface area using the fact that this is my surface area formula. So now for subbing in for my length, breadth, and height, I'm going to be subbing in 2 times those distances because my scale factor is 2. My scale factor being 2 means that each side has been multiplied by the scale factor. So each side's been multiplied by 2. So you can see here I've replaced the length, breadth, and height, each with being multiplied by 2. And this simplifies to 8 length breadths plus 8 length times heights plus 8 base times height. But the main thing that I want you to see, what's interesting, is if I look at the difference between my original formula and what the result of multiplying by the scale factor did, we can actually see that it's now 4 times the original formula if I take a highest common factor of 4 out. So I'm going to ask you guys to start seeing if you can see a link between the scale factor and how this relates to how I can express the new surface area of a particular shape. Cool. Let's look at what happens to the volume. Now instead of length times breadth times height, I now have 2 lengths times 2 breadths times 2 heights. And this gives me a result of 8 length times breadth times height. Also, everyone, I'm going to start asking if you see any connections between the relationship of the new volume and the scale factor. So I want you to start looking, is there any connection at all between the scale factor and how I can write the new volume? Let's look at another example with a different scale factor. So the next scale factor that we are going to be looking at is 4. Similarly, we are going to be multiplying the length, the breadth, and the height by 4, and those are going to be substituted in to the formulas where we've got length, breadth, and height present. So again, all I've done is replace all of those distances with 4 times that distance. This simplifies to be 32 lb plus 32 lh plus 32 bh. Again, guys, is there any way that I can express this new surface area in terms of my old surface area? My old surface area is the normal formula, and if I want to try and see what the connection is, if I take out a highest common factor of 16, I can see that the scale factor of 4 led to my surface area being 16 times the original surface area. So again, I'm going to ask you to put your thinking caps on. Is there a link between these two? Similarly, for the volume, I've substituted in the new distances, and I got 64 times the original volume. Is there any link between the scale factor and the new volume? I want you to start thinking. We're going to talk about it just now, but I'm hoping that someone's going to catch it before I say it. Great, let's look at another scale factor. So the next one is a scale factor of a half. So before we continue, just in case the half is throwing you off, it is possible for me to reduce the dimensions. So obviously, I can imagine a box being 2 times larger, but also I can imagine the lengths of a box and the dimensions of a box being half that size. So instead of doubling or tripling or quadrupling the lengths, we are now halving the length, the breadth, and the height. So it is possible to have a fraction as your scale factor. Let's see what it does to the surface area and the volume. So we've now got a half length, half breadth, half height. Again, substituting it into the old formula, and again, trying to see, is there a link between the old expression for surface area and the way that I can write it in terms of the new one? And everyone can hopefully see that if I take a quarter out as a highest common factor, I can see that a quarter times the old surface area is an expression for the new surface area. Again, if I look at the lengths, what is the relationship between a half and a quarter? Well, it is a half squared. And if I look at my previous slide, I'm sure that everyone will agree that I can see that my surface area was affected by the scale factor being squared. So I'm hoping that everyone's starting to see a bit of a pattern, that the scale factor squared can be multiplied by the surface area to get the new surface area. So let's now look at the volume connection. Again, just substituting in the dimensions affected by the scale factor. It's equal to 1/8 times length times breadth times height. I'm going to ask you guys to carry on thinking about the link between the scale factor and the volume question. We're going to discuss this one on the next slide. So, for this next one, I've done a very similar process, except now I've substituted in 10. We can see that the scale factor influenced the surface area in a way that it is going to be 100 times the original surface area. So in general, everyone, we can see that the surface area of a three-dimensional shape, and in this case it is going to be the rectangular prism, the scale factor squared times the old surface area is representative of my new surface area. Let's look at the link between the scale factor and the volume. We can see that 1,000 is actually 10 cubed. And if we look at this connection between the scale factor and the new volume is equal to the scale factor cubed times the old volume. Cool, guys? So, in general, we can say that if the length, breadth, and height of a rectangular prism have been multiplied by a scale factor of k, then the surface area will be multiplied by k squared, and the volume will be multiplied by k cubed. Great, everyone. I hope that everyone's with me. We're now going to be going into an example to look at how we can actually calculate surface area and volume using a scale factor. Let's go to the example. So guys, for this question, we have been given a rectangular prism. We are first going to calculate the volume of the particular rectangular prism. Then we're going to calculate the volume of the rectangular prism if the length, height, and breadth are multiplied by a scale factor of 2. For C, we're going to calculate the surface area of the rectangular prism. And then D, we're going to calculate the surface area of the rectangular prism if the length, breadth, and height are multiplied by a scale factor of 3. Let's get going. So, we're first going to calculate the volume of this particular rectangular prism. And luckily, this is a straight substitution. It's our area of our base, which is length times breadth times our height. Something that can help, you don't have to do this, but it is a recommendation, is what I would do is just write what my length is, what my breadth is, and what my height is for this example, just so when I'm substituting it in, it's fairly clear as to which values go where. So my length is 11, my breadth is 3, and my height is 4. So I'm going to end up having my length times my breadth times my height. And this is going to give me an answer of 132 centimeters cubed. Please remember, it is centimeters cubed because this is a volume. Let's go to B. So it says, calculate the volume of the rectangular prism if the length, height, and breadth are multiplied by a scale factor of 2. So everyone, please remember that this means that now we're going to have 22 centimeters as our length, 6 centimeters as our breadth, and 8 centimeters as our height, because it has been multiplied by a scale factor of 2, which means I am doubling all of my lengths. There are two ways to go about this. You can either say 8 times 22 times 6, because these are your new values for the volume. Or we can use the knowledge that we know that the volume of a rectangular prism is k cubed, where k is my scale factor, times length times breadth times height. So my scale factor is 2, so I know 2 cubed times my original volume of my rectangular prism, which if I fetch from the other side, I can see it's 132 centimeters, so I'm going to carry that forward. So it's going to be 2 cubed times 132, because my scale factor influences my volume, as my scale factor cubed times the volume gives me my new volume. So let's pop that into the calculator. So I'm going to have 2 to the power of 3, 2 cubed, multiplied by 132. So my new volume is 1,056 centimeters cubed. Great, everyone. I hope that you're with me so far. Just remember that when I've got a scale factor influencing a rectangular prism, it is going to be the scale factor cubed multiplied by the original volume. Let's go to the next part of the question. So we are now going to calculate the surface area of the particular rectangular prism. Again, I'm just going to write my length is 11, my breadth is 3, and my height is 4. So we again need to take the area of all of the different rectangles that make up this particular prism. So I'm going to have 2 times 11 times 3 plus 2 times my length times my height, which is 4. Then I'm going to have plus 2 times my breadth, which is 3, times my height, which is 4. So I've now substituted in the length, the breadth, and the height to get the area of all of these rectangles. Now I'm going to plug it all into my calculator just so I can get a final answer. So it's going to be 2 times 11 times 3 plus 2 times 11 times 4 plus 2 times 3 times 4. So my surface area is 178 centimeters squared. Just a reminder, because it is the surface area and it's adding the area of the 6 surfaces that make up the rectangular prism, the units are squared. It's only cubed for volume. Let's go to the next part of the question. So we are now going to calculate the surface area of the rectangular prism if the length, height, and breadth are multiplied by a scale factor of 3. Just a reminder what we said, the influence of the scale factor is on the surface area. We said that the scale factor squared multiplied by the surface area will give me the new surface area. So my scale factor squared will be 9, because it's 3 squared, and I'm going to multiply it by my original surface area, which is 178. So I'm going to have 9 times 178 in order to find my new surface area, which is 1,602 centimeters squared. Welcome back, everyone. Before the break, we had started to talk about the role of the scale factor on a rectangle, as well as the role of a scale factor on the surface area and volume of a rectangular prism. In this part of the lesson, we're going to look at the role of a scale factor with some other polyhedrons. Let's go to the board. So guys, in this segment, I'm going to remind you that a scale factor is a number that I multiply any of my dimensions by with regards to a shape. I'm also quickly going to remind you what a polyhedron is. Then we're going to go into scale factors affecting cylinders as well as scale factors affecting spheres and cones. Great. So just a reminder, a polyhedron is a three-dimensional figure with 4 or more flat surfaces. Great. Now let's have a look at the surface area and volume of a cylinder. This is just a reminder of formulas that you have done in the past. Surface area, we add together the exterior shapes that make up the three-dimensional shape. So I'm going to add the area of the two circles, which we know are pi r squared, because that is the area of a circle. So the area of the two circles will give me 2 pi r squared. Then we're going to take the area of the rectangle that wraps around the cylinder, and that area is 2 pi r times h. So just a reminder that that is the surface area of a cylinder. The volume of a cylinder is the area of the base, and the base is a circle. So it's pi r squared, and this is multiplied by my perpendicular height. So the volume of a cylinder is pi r squared times height. So I'm going to ask you to predict what will happen to the surface area of a cylinder if the radius and the height are both multiplied by a scale factor of k. So everyone, for this particular example, I'm going to ask what you think would happen if I multiplied the height as well as the radius by a scale factor of k. What do you think would happen? Let's go to the board. So if the radius and the height are multiplied by a scale factor of k, then my new radius will be kr because it's k times r, and my new height will be kh. So I'm now going to substitute kr in place for my radius and kh in place for my height. So I'm going to have 2 pi times my radius squared, and my new radius is kr, so it's going to be kr squared, plus 2 pi times my new radius, which is kr, and my new height is kh. So if I simplify this, it's going to be 2 pi k squared r squared plus 2 pi k squared rh. So all that I've done is simplify, but is there a way that I can express the new surface area in terms of the old surface area? Is there a connection between this line and this line? I'm going to give you a second to see if there's a way I can express the new in terms of the old. Hopefully, everyone can see that I can take out a highest common factor of k squared because I have a k squared present in both cases. So it's going to be k squared times 2 pi r squared plus 2 pi rh. So guys, for a cylinder, when I increase the height and the radius by a scale factor of k, this affects the surface area of the cylinder. The new cylinder volume will be k squared times the old cylinder surface area. So the new surface area is going to be k squared times the old surface area. Great, let's go to the board. So now that we've seen what happens with the surface area, we are going to predict what will happen to the volume of a cylinder if the radius and the height are multiplied by a scale factor of k. So I'm going to ask everyone to think. If I calculate the volume normally, what will the difference be if I now multiply the height and the radius by a scale factor of k? How is that going to affect my volume? Cool. Let's see if any of your ideas are proved correct. So, because I've multiplied by a scale factor of k, My new radius is kr, and my new height is kh. Just a reminder that the volume of a cylinder is equal to pi r squared, which is the area of the bottom circle, multiplied by the height. So the area of the bottom circle multiplied by the perpendicular height. But I now have new expressions for my new radius and my new height, and those are kr and kh. So all I've done is replace my radius with kr, and I've replaced my height with kh. So my new volume will be pi k squared r squared times kh. And if I simplify that one line further, it's going to be pi k cubed r squared h. Now everyone, I'm going to ask you, is there a link between my old volume and my new volume using the fact that I've multiplied by a scale factor of k? Is there a link? Okay. Also, one way to see what the link is to maybe see what the difference is. So the initial volume is pi r squared times the height, but this one is pi k cubed r squared times the height. So we now have a k cubed present. And if I take this out as the highest common factor, it's going to be k cubed times pi r squared h. So I can see that the influence of the scale factor multiplied the new volume to be an expression as the old volume multiplied by k cubed. So guys, in general, if the radius of the circular base and the height of a cylinder have been multiplied by a scale factor of k, then I can generalize that the surface area will be multiplied by k squared and that the volume will be multiplied by k cubed. Great, guys. I hope that everyone's with me. We're going to move on to the next slide. So we're now going to look at the surface area and the volume of a sphere. Just a reminder that the surface area is 4 pi r squared and the volume is 4 over 3 pi r cubed. So I'm going to ask you, what do you think would happen to the surface area and the volume of a sphere if the radius is multiplied by a scale factor of k? So knowing that my surface area of my cylinder was affected as it was multiplied by k squared, and the volume of my cylinder changed as it was multiplied by k cubed, do you think there could possibly be a link between how a scale factor affects the surface area of a three-dimensional figure and the volume of a three-dimensional figure? Is there any connection between what k does to the surface area and the volume? I'm hoping that your brain is getting some ideas. Let's go to the board to see what happens. So we are going to test our predictions for a scale factor of 2 and a scale factor of 4. So if you think that there is going to be a similarity, that means that my surface area is going to be multiplied by k squared. So if there's going to be any kind of connection, we're going to see if my new surface area is multiplied by k squared. So my scale factor is 2, so it would be 4 times it. And for volume, we want to see if my k factor is going to have an effect on it. And that would be k cubed. Great, guys. So we are now going to test to see if we are right. So previously, the new surface area was affected where the new surface area was k squared times the surface area, where k is the scale factor. So I want to see if my new surface area is going to be my scale factor squared, which is 4, times the original surface area, which is 4 pi r squared. So I want to see if my theory is going to be correct if my scale factor squared times the new surface area is the actual new surface area. Then I'm going to test my theory to see if my scale factor cubed multiplied by the original volume is the new volume. So 2 cubed is 8. So we're going to see if my new volume is equal to 8 times my old volume. Similarly, I'm going to see if my scale factor squared, so 4 squared is 16, multiplied by my old surface area is equal to my new surface area. I'm also going to investigate to see whether my scale factor cubed, and in this case it will be 64 because 4 cubed is 64, being multiplied by my volume is representative of my new volume. So everyone, we've now hypothesized about what we think the new volume will be and what the new surface area will be. In the next slide, I've actually shown you the calculations so we can see if our theory is correct. Let's go back to the board. So now for the scale factors, I have actually written that the new r is 2r because I've multiplied it by a scale factor of 2. And if I substitute it into the formula, I can see that it becomes 4 pi times 4 times r squared, which is just 4 times my original surface area. So my theory was correct. It is my scale factor squared times the old surface area to get the new surface area. With the volume, we can see that it actually was true, that by substituting in 2r is my new radius, my new volume is 8 times my old volume. So again, the scale factor cubed times the old volume is the new volume. The exact same thing happened when my scale factor was 4. I have my scale factor squared times my old surface area to get my new surface area. And then similarly, I've got my scale factor cubed that represents my new volume because the scale factor cubed times the old volume is the new volume. So let's go to the next slide. In general, if the radius of the sphere has been multiplied by a scale factor of k, then the surface area will be multiplied by k squared and the volume will be multiplied by k cubed. Let's move on to the next slide. The surface area and volume of a cone. So initially what's going to happen is I'm just going to remind you of the formulas. The volume of a cone is 1/3 pi r squared times height, and the surface area of a cone is pi r length plus pi r squared. So we are now going to predict what happens to the volume of the cone if the radius and the height are multiplied by a scale factor of k. So everyone, previously we know what happened with the scale factor of k with regards to volume. Often it was the case that the new volume was the scale factor cubed times the old volume. So I'm going to see if it happens again. Let's go back to the board. So our prediction is that the new volume of the cone will be k cubed times the old volume, which is 1/3 pi r squared h. Great, everyone. So we've hypothesized that the volume of a cone will be multiplied by k cubed. The next part of this actual lesson, we're going to see what happens to the surface area when I multiply each of my dimensions by a scale factor of k. We're going to see if it's the same thing or if there are any differences. But we'll do that straight after the break. Hello everyone, welcome back. Before the break, we were looking at the surface area and the volume of a cone. We predicted that if I've introduced a scale factor of k to the height and the radius of a cone, that the volume would be affected in a way that the new volume would be k cubed times the old volume. We're now going to see if we can make any predictions or any conclusions about the surface area of a cone when a scale factor has been introduced. Let's go to the board. So, if the radius and the height of a cone are multiplied by a scale factor of k, explain why the surface area does not increase by a scale factor of k. So this is throwing a bit of a spanner in the works, everyone. We want to know, why is a cone special? Why is this the special case of the surface area not being multiplied by k squared? We're going to talk about why now, but firstly on my diagram I want to account for the fact that my radius has been multiplied by a scale factor of k, so that will be rk, and I also want to account for my height being multiplied by a scale factor of k, so it will be kh. We want to know, why is the surface area of a cone the exception to this rule? So the surface area of the cone is equal to pi rl plus pi r squared. But my new height is kh and my new radius is kr. If I substitute this in, it's going to be pi times krl plus pi times kr squared. If I make this line slightly easier, it's going to be pi krl plus pi k squared r squared. Normally in the past we've seen that often I can take a k squared out as a highest common factor and then generalizing that the surface area is multiplied by k squared to get the new surface area, but this one has an issue, and I'm going to ask you why you think there's an issue. We don't have a k squared present in the first term. Why don't we have a k squared present? Well, the first term has the presence of a length. And if I go back to my diagram, my length has not been multiplied by a scale factor of k. So my height has changed by a scale factor of k, and my radius has changed by a scale factor of k. So it's grown in perpendicular height and radius, but my length has not changed. So because my length has not changed, this is not a k squared. So the surface area of a cone cannot be generalized to be k squared times the old surface area equal to the new surface area. So please remember that as an exception. Great, guys, let's go to another example. So we are now going to calculate the volume of the cylinder if the radius and height are multiplied by a scale factor of 3. So guys, I am going to go and write down what my new radius and my new height are. My new height would be 3 times my old height. So my new height would now be 30 centimeters. My new radius is going to be 3 times my old radius. So this is going to be 9 centimeters. So the scale factor of 3 has led me to multiply my height and my radius by 3. I'm now going to substitute this in, so it's going to be pi times my radius squared, which is 9 squared, multiplied by my height, which is 30. And I'm just going to get my calculator out so I can do this. So we have pi multiplied by 9 squared times 30. And this is going to give me 2430 pi. And if I want to simplify this according to the second decimal place, I'm going to press my SD button, and it's going to give me 7634,07. And this is going to be centimeters cubed because it is a volume. Great, let's go on to the next part of the example. I've been asked to now calculate the surface area of the cylinder. I'm going to substitute in my original dimensions because there's no mention of a scale factor. So I'm going to calculate the surface area of the cylinder with my radius being 3, and my height being 10. So I'm going to have 2 pi times my radius squared plus 2 pi times my radius times my height. Let's pop this into the calculator. So we are going to have 2 pi times 9, because 3 squared is 9, plus 2 pi times 3 times 10. This is going to give me 78 pi. And if I simplify this to the second decimal place, it's going to give me 245,04. So my surface area of my cylinder is 245,04 centimeters squared. So let's look at C. We're now asked to calculate the surface area of the cylinder if the radius and the height are multiplied by a scale factor of 4. So there are two ways that I could do this, guys. Just a reminder, when I had a cylinder where it had been changed by a scale factor, the surface area was always the scale factor squared times the original surface area to get to the new one. So the way that I'm going to suggest that we do this is we know that it's going to be equal to 4 squared times the original surface area, because the scale factor squared times the original surface area gives me the new surface area. Another way you could do it is say that my new radius multiplied by a scale factor of 4 would be 12, and my new height would be 40, because it's 10 times 4. But this way is slightly easier because I know that 4 squared is 16, and luckily for the previous slide I calculated my answer, which was 245,04. So it's going to be my scale factor squared times my old surface area to get my new surface area. So this just has to be multiplied by 16 to get my new surface area. And if I do that to the second decimal place, it's going to be 3920,71 centimeters squared. Great, everyone. Thank you so much for joining me for my lesson on scale factors today. I hope that you've enjoyed it, and I hope the rest of your day goes really well.